Good morning, everybody, and thanks for joining us for today's webinar, where we're going to be talking through our hydraulic fracturing fluid optimization program. In this webinar, I'll be moderating. My name is Stuart Kinnair, the CEO and co-founder of Interface Fluidics, and the person walking you through the technology today is Ali Abedini, our Executive Vice President for Technical Operations. Throughout the webinar, please feel free to submit questions through the YouTube chat function or by sending an email to webinar@interfacefluidics.com. Additionally, follow along with us on our social media pages on LinkedIn or on Twitter to keep updated from Interface Fluidics. Interface Fluidics provides unique insights into the interactions and properties of reservoir fluids to help our customers improve their operating efficiencies and enable better long-term decisions for their reservoirs and assets. Our laboratory facility is located at the National Institute for Nanotechnology in Edmonton, Alberta, and our corporate headquarters is in Calgary. We have a long history of working in many reservoirs around the world. Just a snapshot are shown on the screen here. We provide solutions to reservoirs of all kinds. Our technology allows us to measure how fluids behave in porous media by looking at frac fluid optimization, which will be the topic of today's conversation. But we also look at enhanced oil recovery, whether that's chemical, gas injection, anything else you can imagine, or SAGDs, more of a specialty in Alberta, but something we've had a long history with. Going forward, Interface also provides PVT and phase behavior data. Specifically, working on minimum miscibility pressure and MME experiments to help facilitate CO2 sequestration and gas injection, as well as measuring wax and asphaltene appearance conditions and measuring the diffusion coefficient of various fluids. With that, I'll turn it over to Ali here to walk you through how we optimize fracturing fluid.
Thank you, Stuart. Hello, everyone. Today, I'll be talking about the Interface platform and how basically we use it in order to optimize the frac fluid for hydraulic frac operations. A bit about the basics of the interface. So microfluidics is the foundation of the technology that it used at Interface. Fundamentally, microfluidics is the study of the fluid behavior at the macro and nano scale, which is very relevant to the geometries and the porous spaces that we have in the hydrocarbon reservoirs. In terms of the operations, what we typically do, we design and fabricate synthetic, basically porous space or porous media on our silicon substrate. And then once everything is finalized, we do the experiments using the reservoir fluids. And during the process, we use our optical platform in order to visualize the fluid flow into the porous media and then try to probe the interactions and fluid behavior at reservoir relevant pressure and temperatures. Just delving more into the process, how we do our experiments and testing. The first step is the reservoir analog design. What we do in this step, we use the information from the reservoir. We typically use the pore throat size distribution and grain size distribution as well, basically the MICP data, porosity and permeability, and also the wettability of the rock. And if basically there are more information such as the SCM images, thin sections that can help us in order to improve the quality of the reservoir analog, they'll be helpful, especially that will help us to match the morphology of the grains and pores. So once the reservoir analog is designed, we actually do the fabrication. We do it in-house. We have our fabrication experts in order to fabricate and make these analogs. Once the analog is ready, the next phase is actually applying the test and experiments by the representative fluid. So we use the reservoir brine, reservoir oil, and we run all of the experiments at high pressure and temperatures in order to make sure that the results that we get can be used once they're applied into the actual field operations. And lastly, we actually use our in-house developed image analysis algorithm in order to analyze the data and convert all the basically visualization that we we capture during the experiment into the data that can be used for further studies and decision making. In terms of the testing capabilities, specifically for the flowback or fluid flow optimization, we are operating up to 20 MPa or 3,500 psi, and the temperature can go up to 150 degrees of centigrade or 300 degrees Fahrenheit. Of course, for PVT and SAGD operations, we have different operational conditions and capabilities. I think everyone in this webinar pretty much familiar with the frac job. So the idea is to increase the permeability near the wellbore in order to facilitate the oil mobility and having a better production from the reservoir. What we do at interface, we're trying to mimic or replicate the connectivity of the frac and matrix. So as you see in the top right, there is actually a snapshot or zoom-in image of our microfluidics analog, which is a dual porosity, dual permeability system. The triangle shape there is actually replicating the frac zone. As you can see, it has much coarser grains and deeper pore sizes, which generate much bigger porosity and permeability. But the rest of the system is actually the matrix, which consists of basic pore network and the isolated pores. In terms of the porosity and permeability contrast, the matrix has around nano to micro darcies, depending on the size of the throat permeability, and around under 6% porosity, while the frac zone has around 50 to 60 darcies and 30 to 40% porosity. So there is a huge contrast in terms of the pore geometries and characteristics for frac and matrix. How we run our experiment, the bottom graph shows the schematic of the experimental setup that we have. Initially, we saturate the analog with formation brine and oil. Of course, depending on the initial wettability of the rock, we can modify the surface wetting condition of our analogs. And once everything is set at reservoir temperature, we inject the frac fluid, could be a slick water or slick water plus any additives from frac zone into the matrix. So in the picture from top to bottom. And during that process, we measure or track the oil saturation, and we can also quantify the displacement efficiency. It means that how much of the system has been cleared by the frac fluid, which can show how much porous spaces are going to be impacted by frac fluid. And once injection is done, we apply the soak period of around 1 to 2 hours, and then we do the oil flow back by injecting the oil from matrix into the frac zone. So in the bottom picture from bottom to right, bottom to top. So during that period, what we measure first is the amount of the volume which is passing through the system, and we use it as a primary metric to quantify the performance of different cases. We can also measure the regain saturation, and in the end of the experiment, what we can do some sort of pore scale imaging and quantify the change of the contact angle, or how the wettability of the rock has been changed as a function of different additives. So advantages are clear. We can test these experiments at relevant pressure, temperature, and true nano confinement. It's much faster. Each test typically take a day, and we just use very small amount of volume of the fluid, under 200 cc for a big test matrix, and it's highly scalable. And the interesting part here is that the results that you get today, you can compare against in the future. So again, just to highlight the performance metrics that we measure actually in our experiments. The first one is the volume of the oil flowed back. So this is something that we measure optically, given the very small and tiny volume of these microfluidic setups. So for example, for this frac fluid analog, we are looking around 17 to 20 nanoliters. So there's no external device that can measure such a tiny volume. So we have to measure everything optically. So that volume is measure optically through our system, as it's shown in the figure. So as you can see, after the frac zone, there's some sort of the accumulation channels over there that fluid or the oil is being accumulated there, and then we take the images over time and convert them into the volume. So there are other secondary flow dynamic measurements that we do. One is the displacement efficiency that which is measured during the injection part of the process. We do the regain saturation once the flowback is finalized, and also, as I mentioned, we can look at how much wettability modification or even wettability damage we get as a function of different additives. So here is just a sample video. The top video shows the injection of the frac into the matrix from left to right. As you can see, the frac fluid is clearing the frac zone, and also it's displacing the oil from the pores. So through that process, we can measure how much oil has been displaced and then quantify the displacement efficiency. And the bottom video is actually doing the oil flow back. So here the oil is injecting from right to left, and you can see how basically the fluid dynamics go here. So the front of the oil, and then how much of the pore space is being filled by injecting the oil from matrix into the frac zone. So here is a live video of the experiment. So here we have 7 different additives against the control case, which is just pure brine. And you can see the volume of the oil as a function of the time for 8 different cases. So as I mentioned, we record the volume into which is accumulated in the accumulation channels, and we convert them to the volume. So specifically here, as you can see, the control is actually the black color, and then the colorful colors over there, they're basically for additives. So you can clearly see that there's a huge difference between each case. So for example, here, control produced 21 nanoliters, which is actually the lowest amount of the volume, and all the additives, they somehow perform better than the control case, but with varying degrees. Sample P4, the last sample, so it actually produced 89 nanoliters of the oil, and which over 300% improvement over the control case. One thing that I need to mention here, so all of these experiments, they are run at the same condition. We apply the same pressure drop for all of these cases under the same time frame, so the results can be compared with each other really effectively. For this specific system, we actually use the 85 nanometers pore throat size analog, which is around 1 microdarcy pair. And here, all the additives are tested at 0.5 GPT concentrations. So here are some of the basically the results that we've got. So first, on the volume of the oil flowback, as I showed in the previous slide, but here is just the final volumes and the improvement over the control. So you can clearly see that sample P4 performs significantly better than the control, and also than the rest of the additives that we've got here. Of course, you've got some other samples, for example, sample P4, which produced significantly higher than the control case. In terms of the repeatability, you can see the error bands over there. They're fairly tight, and the good piece with this microfluidic technology, and specifically for this analog design, we are able to run multiples just to make sure that the results that we get are consistent throughout the experiment. So the next KPI is the displacement efficiency. So here is actually the parameter that shows how much of the system has been cleaned by injecting the frac fluid during the injection time. So we actually quantify the displacement efficiency both in the frac and matrix. So typically in the frac zone, we don't see a significant differences between all the cases. The reason is the frac is pretty big. It's very permeable. So the fluid displacement should be much easier, but when it goes into the matrix, where basically the system is much tighter, you can see more differentiation between the additives and also against the control. So sample P4 again shows that it has a really good displacement efficiency, but again, there's some other cases that has been showing a good displacement efficiency during the injection process. The next is the regain oil saturation. So here the regain oil saturation is the difference between the oil saturation at the end of the injection and the flowback. So it somehow shows how much of the oil has been mobile during the injection flowback. So again, as you can see, so again, we can quantify both frac and matrix. And you can see that, again, sample P4 has got the highest regain oil saturation in line with the highest oil volume produced and also the displacement efficiency. And lastly is the wettability modification. So all these experiments, they were run at weak oil wet, initial weak oil wet conditions. So the initial contact angle that we made after the modifying the surface condition was around 100 degrees. And once the experiment is done, basically once the flowback is finished, we are taking a lot of pore scale images in the frac zone, and then we measure the contact angle, see if there's any difference, any improvement, or any damage. So throughout the entire experiments that we did here, so we didn't see much difference in the initial and final contact angle. So we don't expect that the contact angle has been changed or the wettability has been either improved or damaged. Just how we measure the contact angle for if you guys are interested to know. So we take high resolution optical images in the frac zone because there's a better optical access to the interfaces of the fluids. So you can see in this picture, which is the actual picture of the process. So the bright color or the greenish color is oil, and the non-oil phase doesn't show here because we actually use a fluorescent microscopy. So we can clearly show the interface and the meniscus of the system, and then by drawing the tangential lines, we are able to measure the contact angle. What we do, we typically measure the contact angle at least for 10 different interfaces. It can be more depending on how many well-cleared interfaces we can get throughout the experiment, but we make sure that basically there is a good histogram of the interfaces throughout the experiments, and then we take an average of the contact angles to report here. So the results that I've shown so far, they were actually part of the work that we did with Primex, an operator down in Houston, Texas. So again, we tried to replicate the Wolfram analog. So that's why we picked 85 nanometers pore throat size. All the experiments, they were run at 150 degrees of Fahrenheit, 3300 PSI. And we use the actual fluid samples, including the oil and the formation brine. Basically, the project was much bigger than what we are presenting here. This is actually the result that you see here is a half of the project. We tested all the chemistries at both 5.5 GPT and then 1.5 GPT. We literally triplicated the loading just to see the impact of the surfactant concentration. And the result was quite interesting. So again, once we increase the loading of the additives, we still found that sample P4 produced the maximum amount of the oil. So still it's the best performer. And overall, we found that the improvement factor or the performance of the flowback has been increased by increasing the concentration. But the interesting result was sample P4 actually, the performance is being reduced as we increase the concentration from 0.5 GPT to 1.5 GPT. So what it shows is basically there's no universal agreement that basically once we increase the concentration, the performance goes better. So sample P4 shows this is not the case. So for specific hydrofrac operations, depending on the reservoir geometries, we may need to look at the impact of the concentration and trying to find the sweet spot or the most optimum concentration, just to make sure that we don't overcapitalize our wells just by increasing the concentration while we are not getting much fluid out. What Primex did, actually, they took this information and tried to apply into a new well that they completed. So here is the 6-month production data of a new well, which was completed with sample P4 at 0.5 GPT and compared with a sister well. So here is well A, which was completed with the other one of the other basically additives at 1.5 GPT. So as you can see, over the 6 months of production, first of all, there wasn't any damage caused by the new completed well with the new surfactants compared to the old ones. But of course, we see that there's around 10,000 barrel of the oil extra production, I guess, over 6 months of period. We are not claiming that it's just because of the surfactant, but that could be a reason. The other interesting part was Primex reduced the chemical cost by over 50% because they actually changed the selection of the chemistry, and also they changed the loading. They actually reduced it by 300% from 1.5 to 0.5 GPT. The other thing that we see here in terms of the peak of the flow rate or the production rate, you can see that the new well, which was completed with sample P4 at 0.5 GPT, reached the maximum production rate at around 20 days of the operations or the flowback, while for the older well, we see around 35 to 40 days. So that could be another indication of basically this chemistry can have impact on faster oil flowback compared to the other well, which was completed with the other chemistry. That's all on the frac optimization. But what we've been doing recently at Interface, we are developing a new technology, new platform that we call it Regain Conductivity. And basically, this testing is a really good complementary testing to our frac fluid optimization, as the goal here is to look at the formation damage caused by the friction reducers inside the frac. Again, unlike the flowback analog, which the idea was to replicate the connectivity of the frac and matrix. So here the goal is just focusing the frac zone and see how much damage we get as a function of different friction reducers and whether the performance can be improved if we add breakers or not. So here, this is the whole idea. So in terms of the testing, so we inject a base case, which is a brine, and then we inject the FR solution, and again we follow up with the second brine injection, and then we measure the pressure drop over the course of the experiment, and also the final stable pressure drop, and then we can provide the damage factor or the conductivity of the frac zone over time, and also at equilibrium condition. So the idea here is to have a test system similar to Propan Pack that's been using in industry, but we've got a lot of advantages here. So it's very repeatable. I'll show the results, and it's much faster than the standard testing in the industry. The cost of the operation is much lower, and we literally use a very little amount of the fluid. So there's also potential for aggregated statistics, means that we can make a really big data set of different friction reducer with different salinities, or if we want to see the impact of the breakers or other additives or not. And it's a very highly scalable process for us. And again, the same as the previous method, the results that we have today, we can compare them against in the future. So here is the snapshot of the result. this is actually work that we did with Oventive in collaboration with them. So we tested 8 different chemistries, basically 8 different friction reducers, and you can see the regained conductivity for each case. So the top bar chart shows the final regained conductivity once everything reaches the equilibrium condition, and you can see the error bands. So they're extremely tight. There is a very crisp differentiation between each cases, including the error bands. And the bottom one shows the dynamics of the regain conductivity over the course of the experiment. So each test basically took around 15 hours, and we almost reached the equilibrium condition after 11 to 12 hours. So again, this is a really good complementary testing to the previous platform that I mentioned. So what we can do, we can optimize the friction reducers through the regain conductivity testing, and then see which one is the best case, and you can then apply it into the frac fluid optimization platform with the other variables, such as if you want to include the breakers or surfactants or other additives within your frac fluid cocktail, and see whether you can improve the overall performance of the oil flowback, or you may see some potential damages as well. To close out, so again, interfaces frac flowback testing enables to optimize your fracturing fluid through better data-driven decisions. So that's our main goal here. And by doing that, we try to make sure that the clients don't prevent the overcapitalization of their wells. So the idea here is not basically injecting as much fluid as we can, but just inject them with a optimum condition. We can also de-risk the operation by mitigating the fluid damage caused by the friction reducer in the completion work. What are the basically solutions to do that? Whether breaker is something that people sometimes add to friction reducers, or they also make some surfactant solution with friction reducer just to see if they can improve the performance once basically the fluid goes into the matrix. And again, the ultimate goal here is to improve the oil recovery from the unconventional reservoirs, and improve the performance of the chemistries that we test. With that, I close the presentation, and I'll be happy to take any questions. So Stuart, it's back to you.
Excellent. Well, thanks, Ali. Very interesting results. It's great to be able to share results that we've partnered with some of our clients on, and be able to show these real world results. So I've been collecting some questions here while you've been speaking, so I'll bring those up. But the first question I have is around error bars. It's not often that you see error bars on data that has flow through porous media. Can you talk a bit about why Interface is able to put error bars on our data where that's not commonly seen in sort of prop and pack testing or core floods?
Yeah. Again, when it comes to the core flood, I myself ran a lot of core flood during my graduate studies. When it comes to the conventional shale formations, due to the extra low permeability of these rocks, it's really challenging to run multiple tests on a shale rock. So time and the operational time frame is something that basically it's overburdening the process. The other thing, typically people use one rock sample, so the rock is going through sequence of washing and cleaning, and they use it for the other tests. So there's a chance to alter the rock properties as they go through different cycles of cleaning and washing. What we have at the interface, as I mentioned, the biggest basically advantage here, the system is small, so we literally can run an injection in, let's say, in a matter of hours rather than days, or sometimes a month if you have the actual tight rock. The other piece, it's worth to touch here now. So for every test, we just use one chip. So we don't clean our chips, we don't resaturate them. So it's just one chip per test. And with that, we make sure that the initial condition for every test and every run is, I can't guarantee 100%, but 99.9% similar. So that will give you a very similar and consistent base to compare against different cases. And because the system is much smaller, the runtime is shorter, so we are able to run basically in duplicates or triplicates, and with that we are able to bring the error bands into our data set. So all of them together, that brings some sort of the advantage to the microfluidic system that can produce much high throughput data compared to the conventional testing oil and gas industry.
Excellent. And then beyond that, the question, I guess that one of the other questions we have is, we talked about surfactants and you talked about friction reducers today. There's a lot of different other chemistries, other kind of novel technologies that people are looking to bring to market and have potentially really huge impacts on the industry. Can you talk about what else have we looked at through our systems, and what are the other sort of technologies that we've evaluated?
Yeah, I mean, again, surfactants is a general term, but basically there's some new surfactant-based solutions, basic chemistries out. The nanofluids, there's some sort of solvent-based surfactants, the bio-based surfactants. Again, we are able to test all of these chemistries in our system. Friction reducers, again, the base is a polymer, so you have a wide range of polymers that people use in designing and synthesizing these friction reducers, so they can all be tested here. Breaker is something else, so you can see whether it can improve or even in some cases may damage the friction reducer, as we saw in some of our testing. There's some other basically additives, such as, I don't know, biocides or clay controls or whatever. So, and the other piece here is that because the system is very suitable for high throughput testing, you can test these chemistries individually, but at the same time you can combine them together. Actually, you literally make the frac fluid pack that you do in the actual operations, and see not only how it improves the performance of the oil flowback, but also how these different chemistries can interact with each other. If surfactant is supposed to improve the performance, is it going to improve the performance the way that it used as a standalone case, or whether if you have it with, let's say, friction reducers or with breakers or with some other solvents, is it going to have the same performance or not? So these are the questions, the wide questions we are able to answer throughout this platform.
That's great. Thanks for talking about the sort of flexibility of the platform there. The last piece, and I wanted to bring up, is the sort of some of the limitations of these systems. Obviously, this is not a real rock, and I know one of our favorite conversations is with geologists. They always ask us, how do you deal with the fact that this isn't a real rock? Can you give us a high level chat about that might pique the interest for the geologists in the room here, of how we deal with that?
Yes, I mean, again, this is a lab testing platform, and you can find a lab testing which is 100% optimum, right? So there are always some sort of deficiencies or some drawbacks with any lab testing, and we are not exception here. So as you mentioned, so there's some sort of limitation here. The system we use is a silicon substrate, so which has this silicon as a main element. So when we are replicating sandstone, so this system is very, very basically it's very good to simulate the sandstone. But when it comes to some other types of rocks, such as carbonate, there's a limitation over there. Our system can't basically capture the reaction between the fluid and rock, so that's one of the drawbacks. So we are looking into it, how we can bring the geology and the mineralogy into the rock, but this is not something that we have commercial at the moment. But the main focus here is just looking at the fluid-fluid interaction at the reservoir confinement. This is the top goal for us. And depending on the type of the rock, we might be able to produce a meaningful data. As I mentioned, for sandstone, it's pretty good. For carbonate, we are not capturing the reaction. At the same time, well, as I mentioned, we are also able to modify the wetting condition of the rock. So, or our substrate, let's say, if it's oil wet, water wet, or intermediate wet, we are able to capture that. And throughout our experiments, we actually saw a lot of additives, surfactants base majorly, that could alter or modify the wetting condition. But overall, short answer, geology and mineralogy is something that cannot be matched in our system pretty well. But what we are good at, we are very efficient in looking at the fluid-fluid interactions at reservoir pressure, temperature, and confinement, and trying to replicate the wetting condition of the rock.
Awesome. Thanks, Ali. And so with that, I think that's the majority of the questions out of place here. Let me just check I think that'll do for now. So with that, I'll say thanks again, Ali. For those of you that are listening and watching, you can reach out to us at info@interfacefluidics.com. Visit our website, interfacefluidics.com, or check us out on LinkedIn. And with that, I will say, if you have any other questions, concerns, if you have an interesting product that needs to get validated, or you've been inundated by a bunch of new products that need to be evaluated, Interface is here to help. We do it fast. We do it inexpensively, so that we can get back to the work of completing wells. So with that, thank you very much.